Okay, we're going to talk about material from lecture 19. Right? This is an introduction to confidence intervals, specifically Z confidence intervals for the population mean. Of course, watching videos is no substitute for reading the book and notes. All right, here's the idea. You need to make an estimate of a population mean, right? Some population mean mu. So what do? You take a sample and you find its mean, right? X bar, and then X bar is the estimate for the population mean mu. What else would you do? It turns out, though, that you can give, in a situation in which you can apply the central limit theorem, that is, if you have a sample size at least 30 or a population approximately normally distributed, in that kind of a situation, you can give a little more information. You can construct what's called a confidence interval to determine how likely it is, let's say, that your estimate for the population mean is pretty good. So here's the idea. Suppose you put the true population mean on a number line. Now, of course, we don't know the true population mean, but let's just suppose it's there. And we start taking samples that we can use the CLT with and to get normality of the X bar variable and so on, right? What will they look like on the number line? Well, you already know because you've seen the central limit theorem. They're going to be normally distributed, approximately normally distributed. If I draw in the PDF for these things, it's going to look like this. Right? That's the X bar curve there. All right. Well, we know, for example, from the empirical rule that 95% of the area under the curve is between these 2 points right here, mu minus 2 sigma and mu plus 2 sigma. Right? Well, what that means is that 95% of all the X bars are within 2 sigma of the population mean mu. Well, that means that 95% of all samples have a mean X bar that is within 2 sigma of the population mean mu. Equivalently, for 95% of samples we could choose of this particular size, for 95% of all those samples, mu is within 2 sigma of X bar. And that allows me to do this. You tell me to estimate the mean, mu, and I say, okay, my estimate is X bar. And what's more, now this is if I know the population standard deviation, sigma. What's more, I can tell you that if I go out to here and here, this would be X bar minus 2 sigma and X bar plus 2 sigma. I can tell you that for 95% of all the samples I could choose, mu would be in this interval around the sample mean. So I express that by saying that I am 95% confident that mu is within 2 sigma of my X bar, in other words, the particular one that I have from my sample. All right, so that gives you some kind of a measure, assuming now that you know the population standard deviation, which we're going to assume for the time being. That gives you some idea of how likely it is that this X bar really is close to the population mean. You would have an actual number for sigma, which would be able to which would allow you to give an actual interval and say, I'm 95% confident that the population mean is in there. All right. Let's make this a little more precise and general at the same time. Suppose I wanted a 90% confidence interval. So what would I do? First thing I would do is draw a picture. So let's suppose this is the population mean mu, and I make the same picture I made before of sample means. So here are some sample means. And of course, they're all piled up around the population mean. And here's the X-bar curve. And what I want a 90% confidence interval. So I want the interval so that 90% of sample means will be in that interval, or equivalently, that this area here is 0.9. I'm going to call the left-hand endpoint of that interval mu minus e, and I'm going to call the right-hand endpoint mu plus e. So 90% of all X-bar for samples of this size are are in the interval mu minus e to mu plus e. Okay. Well, since this is 90% of the area in here and everything is symmetrical, I know that this area is 0.05 and this area is 0.05. So the area to the left of mu plus e in particular is 0.95. Now remember, I'm assuming that we know the population standard deviation sigma. So I could find, if I knew mu, I could find, right? So if I knew mu, you could find mu plus e with inf norm. Right? It would just be inf norm of minus infinity to mu plus e with mean mu and standard deviation sigma. But you can't do that because you don't know mu. Right? It may seem absurd that you know sigma without knowing mu, and in fact that is the case. In almost all cases, you can't even get a decent approximation of one without getting a decent approximation of the other. But this is the way to learn this material, and we will lift that restriction in a later section. Okay, so I know the standard deviation, so if I knew mu, I could definitely find this point right here, which of course would let me find this point and so on. Right? Well, the way around this problem of not knowing mu is to transform this picture to the z-axis. Over on the z-axis, mu here will transform to 0, and these guys will transform to points. They'll be called minus z sub 0.9 and z sub 0.9. That's their official name. These things are the points, right, symmetrical about the mean 0, that bound 90% of the area onto the z-curve, onto the standard normal curve between them. And just like up here, right, this area has to be 0.05, and so the area to the left of z sub 0.9 is 0.95. And over here, I do know the mean and standard deviation, so z sub 0.9 is inf norm of 0.95, comma 0, comma 1, if you like. And that is just about 1.645. Okay. Once I have this point over here, I could transform back to the x-axis and find this point mu plus e, and then that would easily let me find mu minus e and so on. Okay, just want to do this a little more generally now. What I want is a confidence interval for level of confidence C. And remember, I have to assume that the population standard deviation, sigma, is known. All right. So I'm going to start like this. Put mu on a number line, right? And then I'm just going to start putting in a bunch of x bars. So this is really the x bar axis. And I'm putting in a whole bunch of x bars here, sample means, and just to get an idea. And then if I drew the PDF for these things, the x bar curve, it would look like that. Now to get level of confidence C, just like in the things I've done previously, we need the cutoffs for area C in the middle here. If I call this one mu minus E and mu plus E, then the area over the interval from mu minus E to mu plus E has to be C. Now I know sigma, but I don't know mu, so even though I know what this little area has to be, and I'll talk about what it actually is in a second, I know what this little area has to be, right? I can't compute mu plus E directly because I don't know mu. So I do what I did before. I transform this over to the z-axis. And okay, there it is, z-axis. The mean, of course, comes across as 0. Right? It transforms over here as 0. And these 2 points right here are going to be the cutoffs for the middle area C. This one is called minus z sub c, and this one is called z sub c. Okay, this little area here will be the same as this little area here. And what is that? Well, the area in the middle is C, so these two tail parts here, the area in those is 1 minus C, since the area under the whole curve is 1. And so this part of it is 1 minus C over 2. So I can say the area to the left of z sub c is 1 minus that quantity, 1 minus C over 2. And that is just 1 plus C over 2 if you do a little bit of algebra. So z sub c is inf norm of, this is the standard normal, right? 1 plus C over 2, comma 0, comma 1, if you like to do that. Okay, that is how you figure this thing out. That is, these are called the critical values. I'll write that down in a second. These are the critical values for confidence level C. Okay. Once you have z sub c, what do you do with it? Well, you want to transform it back to this x bar axis. Well, the way we're going to approach this is the way we usually do it. We're just going to use the z-score formula. We're going to transform mu plus e over to the z-axis where we know we get this number z sub c. So using the z-score formula, I have z sub c is equal to mu plus e, and of course this is really mu x bar, but they are the same number. Right? Mu plus e minus mu over the standard deviation over here, which is sigma over the square root of n. N, of course, is the sample size. Now, mu plus e minus mu is just e, so I have z sub c is equal to e over sigma over the square root of n. What I'm trying to find is e here. I know this number, right, because I was able to compute it like this. I know this number, I know this number, I know this number, and so I can get what I want here, namely e. It's just z sub c times sigma over the square root of n. Just multiply through there to get it. These numbers, minus z sub c and z sub c, those are the critical values for confidence level C. And E, oops, trying to make it so you can see this here. E is called the margin of error for confidence level C. And when you see pollsters on the TV or whatever talking about margin of error, that's exactly what they mean, this number E here. I'll give you a couple of definitions around this. First of all, a point estimate. A point estimate is just a one-number estimate of a population parameter. Right? So X bar is a point estimate for mu. The sample mean is a point estimate for the population mean. An interval estimate. An interval estimate is an interval supposed to contain the population parameter with a given level of confidence. Right? So an interval estimate is always going to come with a confidence level. And the confidence intervals that we've been working on here, right, those are examples of interval estimates. Okay. I'm going to sum up all the stuff I've been talking about here in a series of steps, right? How to find what's called a Z confidence interval, the kind we've been talking about, for a population mean mu. And this is the only kind of thing we're ever going to do confidence intervals for. Okay, two prerequisites. You must be able to apply the CLT. Right? That is to say, either you have to know that the population is approximately normally distributed, or you have to have been given a large enough sample size to apply the CLT. And secondly, because this is a Z confidence interval, you must know the population standard deviation sigma. All right. Given those things, here are the steps. First, you need to find four quantities. You need to find sigma, n, x bar, and the confidence level C. Second, you want to compute Z sub C, the critical value for confidence level C, and that is just inf norm of 1 plus C over 2. Third step is also a computation. Now that you have the critical value, you can compute the margin of error, E. It's just C sub C times sigma over the square root of n. And then 4, the confidence interval for confidence level C is just the interval x bar minus E to x bar plus E. That's it. Let me do a couple of examples of this. Here's a very straightforward one. A sample of size 36 from a population with standard deviation 3.1 has sample mean x bar equal to 18. Find a 95% confidence interval for the population mean. All right, so let's do step 1. I'm going to need sigma, n, x bar, and C. Sigma, the population standard deviation, has to have been given to you. N, that's 36 here, the sample size. X bar is given to us, it's 18. And C is the confidence level, and of course here I have to write it as a decimal. All right. Step 2, I need to compute the critical value for 95% confidence, z sub c, and that is inv norm of 1 plus c over 2, so this is 1 plus 0.95 over 2. And because I'm inclined to make lots of mistakes in computation, I'm going to do this first addition in my head, and I'm going to write that as 1.95 over 2. And the reason is that if I don't do that, I'm going to forget, when I put this in my calculator, I'm going to forget to add the numerator parts together before I divide by 2. And this is about 1.96. Okay, now that I have that, I can compute the margin of error E. E is just z sub c, this 1.96, times sigma over the square root of n, and there they are, 3.1 over the square root of 36. That turns out to be just about 1.01. I'm sure you can calculate that. Okay, well then, what's the confidence interval here? Right, this is the 95% confidence interval for the mean. It's x bar, which is 18, minus e, 1.01, to x bar plus 1.01. That is to say, it's 16.99 to 19.01. Okay, let me ask you a question. Here's the question. If you chose 1,000 of these samples, the ones we've just been talking about, from the population we've just been talking about, how many of them, approximately, how many of them would have means within 1.01 of mu? Well, you stop and think. What is a 95% confidence interval? Right? Remember, a 95% confidence interval was based on the fact that 95% of all the sample means would be within 1.0. This would be, for example, mu minus 1.01, and this mu plus 1.01. 95% of all the sample means will be in there. Now, the confidence interval is actually constructed around x bar, of course. We actually start with x bar when we construct the confidence interval, and then make this x bar minus 1.01 to x bar plus 1.01. But then 95% of the time, mu is going to be in this interval. So in any case, 95% of these sample means, 95% of all the sample means there are of this size, will be within 1.01 of mu. And so we can expect 95% of them to have this property, right? Or 95% of 1,000 is 950. Okay, let's do another example. 50 measurements of visibility through the water at any one particular location average 25 feet. Find a 90% confidence interval for the mean visibility, assuming that this population standard deviation is 5 feet. So, all right, what are we going to need again? Sigma, n, x bar, c. Sigma, we're given that directly, is the only way we could get it, 5 feet. N is the sample size, and that's 50, because 50 measurements were made. X bar is the sample mean. We're told that these measurements average 25 feet. And C is 0.9 for the 90% confidence interval. Step 2, C sub C, is inv norm of 1 plus C over 2, 1 plus 0.9 over 2, and we use 1.645 to approximate that. Remember, there are two cases in which you round z-scores to 3 decimal places. This is one of them. Okay, third, the margin of error E is just z sub c, 1.645, times sigma over the square root of n. So that is 5 over the square root of 50. And when you work that out, it comes out to be about 1.16. And so finally, the confidence interval is x bar, which is 25, minus e, which is 1.16, to 25 plus 1.16, which is 23.84 to 26.16. All right, that's it for this section.